Yes, sir. We are on live.
Ah,
Dear all, a very good afternoon. I am Dr. Ashish Saturi, and I am delighted to welcome you in this today's event on behalf of Dolphin PG Institute of Biomedical and Natural Sciences, Dehradun. Dolphin PG Institute is an autonomous institute affiliated with HNB Gurwal Central University and has been proudly accredited with A plus grade by NAC in the second cycle of this year. At Dolphin PG Institute, the Department of Physics is committed to bringing esteemed intellectuals from around the world to provide a world class educational experience to our students and the faculty members. Today, we are here to celebrate a significant milestone in India's space journey. As we all know that on August 23rd, 2023, India became the fourth country to land on the moon and the first to reach its southern polar region. To honor this historic achievement, we are celebrating National Space Day 2024 with theme Touching Lives While Touching the Moon, India's Space Saga. In this space, today's talk is more than just a commemoration of our space accomplishment. It is an opportunity to explore the intriguing realm of black holes. These cosmic phenomena, with their complex physics and profound implications for our understanding of the universe, continue to captivate scientists and enthusiasts alike. We are delighted to have Professor Rajaram Nityananda, a leading expert in the astrophysics and a cosmos personality of the intellectual domain of this country. He is joining us to share his insight. Before we dive into today's discussion, it's my honor to introduce this distinguished figure of the intellectual domain of our country. Professor Rajaram Nityananda studied physics at the Vivekananda College at the IIT Chennai and joined Professor S. Ramesan at the National Aeronautical Laboratory, Bengaluru, for a PhD in 1969. After submitting his thesis on topics and a crystallographic to the Bangalore University, he moved to Raman Research Institute in 1975. Over nearly 25 years at RRI, he worked in some areas of condensed matter physics, astronomical optics, image processing, and gravitational dynamics. At the NCRA, TIFR, National Center for Radio Physics and of the Tata Institute of Fundamental Research in Pune, he served as a center director from 2000 to 2010 and worked on problems relating to radio astronomy such as calibration and interference removal and orbit determination. He has taught physics and astronomy at the graduate school level both in Bangalore and in the Pune after a short period of TIFR Hyderabad and ISF Pune in 2011 to 2013. He taught undergraduate physics at Azim Premji University from 2014 to 2021. He has been at the ICTS TIFR International Center for Theoretical Sciences TIFR as a visiting professor since 2022. He is a fellow of the three Indian Science Academies and he served as the editor of Pramana, a prestigious journal of Indian science, Journal of Astrophysics and Astronomy and Resonance. He has keen interest in teaching basic physics and communicating physics and astronomy to general audience. So, without any further ado, I would like to invite Professor Rajam Nityananda for his talk on black holes. And dear audience, thank you for being here, and I hope you will enjoy this enlightening session. If you have any queries, I would like to request you please put them in your chat box, and I would like to request after the talk to Professor Rajaram, definitely he would love to answer your queries. So without any further ado, I would like to invite Professor Rajaram Nityananda. Please, sir, now mic is over to you.
um, Thank you, Dr. Aturi. Uh, it's a pity that I can't be there in Dehradun. It's a very beautiful place, but age and distance are all coming in the way. But this is the next best thing, and I'm going to start my presentation.
Yeah.
Okay. So I
Yes,
hope
sir.
all of you can see this first slide.
Yeah,
It
fine, sir.
simply gives the title, Black Holes, and my name and my affiliation. Of course, this affiliation has only been there for the last 2 years, and perhaps my longest affiliation was at the Raman Research Institute for nearly 24 years, but I have spent quite a bit of time with TIFR as well. Okay, so most people would have heard of black holes because every now and then you see something in the newspapers. So I'd like to introduce the idea, and it's quite an old idea, purely as a flight of imagination by two people towards the end of the 18th century, one in England, uh, John Michel, and the other a little bit later in France. Laplace's name, many of you would have heard in the context of physics and mathematics. Just as a thought experiment, they said, let's increase the radius of the sun and keep its density the same. Incidentally, the density of the sun, it's not as dense as the earth because it's made of gas. Average density of the sun is about 1 gram per centimeter cubed. Or since all of you were educated in SI, maybe 1000 kgs per meter cubed. Now, the same density, if you keep increasing the radius by 500 times, so that's just a thought experiment. So obviously the mass will go up by 500 cube times. Then you can calculate the escape speed. I'll shortly be showing you the small calculation of the escape speed, which is, I think, taught in 12th standard. And then they noticed that the escape speed from the sun would reach the speed of light, which means any slight increase in radius and light cannot escape. So they just said, maybe there are bodies from which light cannot escape, and therefore we cannot see them. So here's the calculation. This is the formula, which I hope all of you remember. Right? It has Newton's constant, mass of the star in the numerator, and radius in the denominator. So if you increase the mass, the escape velocity increases, which is exactly what happened. Radius also increases, of course. And for the Earth, it's 11.2 kilometers per second, not per hour, and 600 kilometers per second for the Sun. Okay, so still much less than the speed of light. So the other way to make the escape velocity reach the speed of light is to keep the mass of the Sun the same, but reduce the radius, right? And you have to reduce it quite a lot because 600 squared has to become 300,000 squared. So you can just take the previous formula and equate to c square and then solve for r. You will get the radius to be twice gn over c squared. Okay. And if you put in the numbers for the sun, right, you will get a radius of 3 kilometers. And this explains to you why stars, ordinary stars, are not black holes. Because the actual radius of the sun is 700,000 kilometers, okay, which is nearly 1 million kilometers. So, in order to make it a black hole, you would have to compress it to 3 kilometers radius. Now, this is a classic case of getting the right answer by a not so correct method, okay? The reason is that Newton's gravity, which is used to do this calculation, was not intended to apply to light. So it was Einstein who studied the behavior of light, first in special relativity and then in his theory of gravitation, which is called general relativity. And I have to apologize for a spelling mistake here. So the same radius emerged in Einstein's theory, but now it was rigorous, okay? And it's called Schwarzschild radius. This last E should be a D, okay? So Schwarzschild is the name of the person who calculated this radius immediately after Einstein proposed his theory. So it's interesting that Einstein didn't calculate that radius. It's his colleague, who was an astronomer, who was able to solve these very complicated equations which Einstein had written down. And he reached the conclusion that an object at this radius, light will not escape. Okay? But this requires a bit of explanation. now I'm doing a kind of fast forward, okay, and then I'll come back to the history. Purely as idea, black holes have been there around for a long time. 1917 is a Schwarzschild's paper, okay. However, if you ask, have we actually seen them, okay, directly? That's what an astronomer would like. Today, the answer is yes, and I'm splitting the answer into two parts. One is on the left here. You can see my cursor. This is a case where we did not actually see the black hole, but we heard the black hole. And I'll explain what heard means. Itchy, listening to the black hole, so to speak. And on the right-hand side, you see a picture of a ring. First of all, I should tell you this is not visible light. It's millimeter waves, okay, short radio waves. And the evidence for the black hole is not this light which is coming out, because light, of course, cannot come out from a black hole. As we will see later, the evidence is this empty dark region in the middle, in which you would have received light, except that it has fallen into the black hole and is unable to come out. Okay. Let me go back. Yeah. Now, let me quickly explain the picture on the left-hand side, but I will have much more to say about the right-hand side picture, because number one is a direct image, and it's carried out using the techniques of radio astronomy, with which I'm much more familiar, thanks to my stay in the Raman Institute and in the NCRA. Okay. But in ICTS, actually, there are many people who work on this kind of problem. So first of all, what is the horizontal axis and what is the vertical axis in these four graphs? Okay. So the horizontal axis is just time, and this is just a few seconds. Okay. The vertical axis is a signal which is obtained by a very, very sensitive instrument called LIGO, LIGO. It took nearly 20 years to build this instrument. It consists of mirrors, long vacuum tubes, and laser beams which move around in these vacuum tubes, which can detect the smallest movement of these mirrors. Sorry. In the laboratory, MSc laboratory, or perhaps even BSc laboratory, you have a setup called Michelson interferometer, where if you move a mirror by, say, half a wavelength, a bright fringe becomes a dark fringe. Now here, this is much, much more sensitive, and though it's hard to believe that the actual movement of the mirrors here is even less than the size of a proton, 10 to the minus 15 meters. Okay, and now this movement, of course, if you see some movement in such a sensitive instrument, it could be just due to some disturbance. But this has now been seen in two instruments which are separated by thousands of kilometers. So clearly, it's not originating from the instrument. It's originating from outside the Earth. Also, the time delay between these two instruments, which shows that whatever is causing this disturbance in the instrument is coming from a different certain direction. And the last piece of evidence is that people had built this instrument expecting to see black holes moving around each other, binary black holes. And they had already calculated what the kind of signal it would be if two black holes go around each other. So what you're seeing is that as they approach each other, the period of the orbit gets shorter and shorter. Okay. And then the strength of the signal gets stronger and stronger. So the period can also be thought of as a frequency, and the frequency is measured in hundreds of hertz, which is why the idea of hearing is quite appropriate, because the sound waves, of course, these are not sound waves. These are gravitational waves. Okay. When such heavy objects go around each other, they disturb the space-time, and something which was calculated by Einstein and others. And so after these two black holes almost touch each other, then we'll say something about the second part, where you have some oscillations and they settle down and become one black hole. And this is such a characteristic signal, it's very unlikely that it could come from any other source. So the entire astronomy community believes that these are two black holes which merged. By the way, the signal was recorded in 2014, but this is such a major event that they had to do a lot of cross checks before they announced it in public, which was in February 2016. And the paper had 1,000 authors because this is such a complex experiment. So I'll just explain these two things below. This is now the same signal, but the intensity of the color shows you how strong the gravitational wave is. And the vertical axis, this is time. And the vertical axis is the frequency. So the frequency goes from few hundred hertz to a few thousand hertz, which is exactly what even a vocal musician would be singing. Okay, so we have truly can say that this experiment, which unfortunately I will not be able to tell you much more about, right? You should get a separate talk on that, and I'm sure some of my colleagues in ICTS would be happy to give a talk on this experiment in which they are the experts. Okay, so this is hearing black holes, but of course, radio astronomers did not want to be left behind. So I will tell you a lot about the efforts to produce this image because it's really the culmination of decades of work. Now, in this case also, the data was taken in 2016, okay? And I'll tell you exactly what kind of data was taken. Again, a big collaboration, 300 authors. But the final announcement was made in 2019 because when you claim that you're seeing a ring of matter around a black hole in a dark region, which is caused by the black hole, you can call it the shadow also, you better make sure that that claim is correct. So different groups try to cross-check. And so this is a very brief introduction to the modern observations of black holes. Now we will again go back. And I told you that Einstein's general theory of relativity predicts these black holes and predicts gravitational waves. So let's go back to say. Now, the special theory of relativity, I can't obviously give you a full course on it, simply says that things cannot travel faster than light. So if you are here and you send out signals, okay, and this is space and the vertical axis is time. So you cannot reach a certain distance until a certain amount of time has elapsed, okay? And if you choose the proper units, this line will be at 45 degrees. Astronomers, for example, like to measure distance in terms of light years, the distance that light would travel in 1 year. So if the vertical axis is in years and the horizontal axis is in light years, then you would have these lines at 45 degrees. And this light cone also is signals which arrive at the observer, and they arrive from a distance, but they need a certain amount of time to reach you. So this has a very interesting consequence that in astronomy, we receive all kinds of signals, light, gravitational waves, and so on, from distant objects. And when they are very far away, we are not seeing them as they are now. We are seeing them in the past. So astronomers are not only looking at the geography of the universe, they are also looking at the history of the universe. So these are the few comments that I wanted to make about this light cones. Okay. Now, this is the first step that Einstein took. Actually, it was he did it in a more algebraic way, and this geometric way of thinking about it is due to a famous mathematician called Minkowski, a few years after Einstein. And history is that Einstein thought this is all unnecessary, but later on he realized it's very valuable. And he gave a theory of gravity, in which gravity simply influences space-time. Now, obviously, I cannot tell you all the details of this theory, the mathematical details. But basically, according to Einstein, the space-time in which we live is made up of these light cones, but they have to be connected in a certain way, right? And if you had to summarize in one sentence, there's a person called Wheeler who said, matter, any mass, tells space-time how to curve. So once you have the curved space-time, matter will move along some particular curves in the space-time. So these two are intimately connected. Now, one person who has, he's no more with us. He passed away in 2017. And is Professor C.V. Visveshwara. Yes, I think I've got, I think he had, there's another H here also, Visveshwara. But anyway, He did his PhD in Maryland with Misner, who was in turn a student of the Wheeler, whom I told you about. And he did some very pioneering work in his thesis. When he started his thesis, people were not sure whether these black holes, although they are solutions of Einstein's equations, whether they are really stable. So to find out there's something stable, you have to disturb it. And then if it oscillates and the oscillations are damped, it's stable. This is a very tough mathematical problem which he solved in his thesis. So the stability of the Schwarzschild black hole is attributed to Visvesvara. Then, of course, he came to India. He was in the Raman Institute, the Indian Institute of Astrophysics, and the Bangalore Planetarium. He was a very fine popularizer of science and in particular relativity. And I'll be showing you 3 slides, which are all cartoons. So he was universally known as Vishu. So that's his signature on the cartoon. So the first part shows this is light traveling and this observer cannot reach it. Okay. If the light is in front of the observer. But if light comes from behind the observer, then the light will cross the observer, but that is it. After that, the observer cannot cross the light again. This diagram you have already seen. Okay. So this is his explanation of special relativity. And the figures I have taken from a very nice popular article, which he wrote in 1979, 100th year of Einstein's birth. It's called Black Holes for Bedtime. It's available on the website of the Bangalore Planetarium. Now, I told you that Einstein explained gravity by the behavior of these light cones. So that is illustrated in this cartoon by Vishu again, right? So here, far away from this mass, the light cones are like this, but as you come closer, the light cones start bending. And at this point, you can only move within the light cone, but you cannot move outwards because, right? So, according to Einstein, and according to this cartoon, if you come, this Schwarzschild radius is a place where all light rays are ingoing. Okay, so you may send the light beam inwards or you may send it outwards, but even the outward going light beam, as far as you are concerned, it will be going outwards because you are really falling inwards. Okay, you are falling inwards. So as far as you are concerned, the light beam is going outward, but as far as an observer at infinity is concerned, at this radius, the light beam is just standing still. So this does not violate what Einstein said in special relativity. It's just that this observer, local observer, sees light traveling outwards, but the distant observer sees this wavefront of light as frozen. Okay. So this cylinder is called the event horizon. The reason is that any event occurring inside this cannot be seen by people outside. So this is the best that I can do in this short period to explain to you how the concept of a black hole arises in Einstein's theory of gravitation. So let us accept that you can have such a radius associated with an object which is sufficiently massive and also has a sufficiently small radius. Now, what happens if this object rotates? Okay, so again, the other pioneering work done by Visvesvara was on rotating black holes. Okay, and the analogy he gives is that the entire space-time around the black hole is rotating. So if you do nothing, you will be dragged along. If you do nothing, but if you don't want to rotate, you will actually have to use some engine or something like that. Okay. So that's an important difference between a non-rotating black hole and a rotating black hole. And I don't know how many of you have read this Alice in Wonderland. And he says it takes all the running you can do to keep in the same place. So with this little introduction and also pointer to Visvesvara's article, Black Holes for Bedtime, I can even share a PDF with Dr. Rathuri so that if you are unable to find it on the Bangalore Planetarium website, same picture. The light cones near a rotating black hole not only tilt toward the black hole, but they tilt in the angular direction. Okay. So the orbits in Newtonian gravity, orbits which are clockwise and counterclockwise are the same, but that's not true. In Einstein's gravity, you have a rotating black hole, the two kinds of orbits would be different. Now, it's all very well to solve the equations of general relativity and make a prediction of black holes, and all this had happened by about 1960s. But this is where the astrophysicists came in. How would you form such a black hole? Okay, so we now have to go back to normal stars like the sun, and they make energy by converting lighter elements into heavier elements. So in what's going on in the sun is conversion of hydrogen to helium. And fortunately, the hydrogen in the sun has not been exhausted, even though the sun has been shining for almost 4.5 billion years. In about an equal amount of time, it will get exhausted. And in the case of the sun, what could happen, I'll tell you later. But in a heavier star, the helium can be pushed. This is the process of nuclear fusion to carbon, and carbon can be pushed to heavier elements and so on. Every one of these reactions releases energy. Because it releases energy, of course, the energy escapes, but the center stays hot. Because the center is hot, it's able to exert pressure, and that is why the star does not collapse. Okay. Otherwise, if you just have so much mass, the different masses will attract each other and the star will collapse. So you need this pressure at the center, and that pressure comes from these heat released by nuclear reactions. But, and the peculiar thing actually is that you would think a massive star would last longer, okay, because it has more fuel. But massive stars, if a star is 10 times the mass of the sun, then it's the energy production is 10,000 times, okay? So actually the lifetime of such a star is 1,000 times less than the mass of a sun. So it's a bit like, a very miserly person having a small amount of money but keeping it for a long time, and a very rich businessman, who maybe sets up a lot of losing companies, losing everything. And once that happens, when the star runs out of nuclear fuel, what happens? Now, interestingly, the answer is actually given by quantum mechanics. You would normally think that quantum physics should only be applied to atoms and nuclei. Okay? However, in the 1930s, people realized that if you have, let's say, the sun, and it has run out of all the hydrogen, so it has got helium in the center, it has all these electrons, and as you keep shrinking it, at some point, there's the uncertainty principle, which tells you that if you reduce the space available to the electron, its momentum will increase. Okay, and of course, the same is true even in an atom, right? So, or in a block of metal which has so many electrons. So, a model can be created without any nuclear energy, where the pressure of these rapidly moving electrons balances gravity. So, this is called a white dwarf star. And the reason is that they've already known stars which are very small in radius and which did not seem to be burning up nuclear energy. Okay. Then the next stage came theoretically. People said, okay, suppose we compress still further, what will happen? Then an interesting thing happens. Many of you may know that the neutron is an unstable particle. It's heavier than the proton. So it decays n going to p plus e, right? There is a positive charge and a negative charge, plus a neutrino, antineutrino actually. So, but if these electrons in the white dwarf star have a lot of energy, then the reaction can go in reverse. And you can convert the protons back to neutrons. So then you will get something like a giant atomic nucleus, and this is called a neutron star. So, as I told you, the white dwarf star as a giant atom was proposed in 1930s, and the neutron star, which is like a giant atomic nucleus. So, just to give you an idea, if you have mass around the mass of the sun, the radius of the sun, I already told you, is about 1 million kilometers. The corresponding white dwarf star would be 10,000 kilometers, right? So, already down by a factor of 100. The corresponding neutron star would be just 10 kilometers, okay, but still not 3 kilometers, huh? Still not a black hole. So these are the end states of stars. I told you white dwarf stars were already known from the late 19th century. The neutron stars were discovered in the 1960s. That again is a fantastic story in itself. done with radio astronomy. Again, I'm sure my colleagues in NCRA, National Center for Radio Astrophysics, would be the right people to tell you about it. How one studies neutron stars using radio waves. But for us, the important thing is, I said that both are routinely detected and studied, but their masses cannot be more than 3 times the mass of the sun. And this is a calculation due to this famous astrophysicist, Subramaniam Chandrasekhar, of Indian origin. He did this calculation when he was very young, 20 years old. People didn't believe him, but he was ultimately proved right. Of course, he had a long career and did many things, settling in the University of Chicago in the United States. Okay. Now, of course, what astronomers tell us is that if the mass of a star is 2 to 8, it will become a white dwarf. Now, white dwarf mass cannot exceed 1.5, so the remainder of the 8 gets pushed out. And that's fortunate because, remember, I told you the star has created some heavy elements. And then these heavy elements can then form the next generation of stars. So all of us have bodies which have carbon, nitrogen. So all these have got pushed out from stars, say less than 8 solar masses, which became white dwarfs, but the outer layers were sent to form a new generation of stars, planets, etc. Then from 8 to 20, the evidence from astronomy is that when these stars, again, the neutron star cannot be more than about 2 or 3 times mass of the sun. So the remainder has to go out. But there's enough energy. When the inner part collapses, it releases, right? And the outer layer is pushed out. Now, this again is fortunate for us because elements like iron and so on are believed to originate in this class of stars. But there could be stars which are more than 20. What happens to that? That's why I said not too heavy stars. So I've already told you about Chandrasekhar and Oppenheimer, Volkoff are the people who did the corresponding calculation for neutron stars. But for more massive stars, no one could come up with an alternative. So for a purely theoretical reason, people said that this is a black hole. It has to form a black hole. But that was just theory. So finally, the detection of gravitational waves, as I told you, that pattern is like a fingerprint. And it would tell you exactly what the masses of these 2 stars are. I should say two black holes. And they came out to be about 30 solar masses. So that is the evidence which we got in 2016, quite late, that this whole picture, the story I have told you is correct. Right? So that is as far as the black holes which originate from very massive stars. Okay. Now I want to move to another kind of black hole. Okay. So this is a picture of what are called Messier objects. Messier is a French astronomer who, in the 18th century, I think, he noticed that many people are trying to discover comets. So whenever they see any fuzzy object in the sky, which is not a star, they say, we have discovered a comet. But many of these objects are not comets. And the evidence that something is a comet is that it should move. Okay, orbits around the sun. It's quite close to us, so it should move. So he made a catalog of all the objects which are fuzzy but not moving. Different kinds of objects, some in our own galaxy, but many of them are galaxies. So this one. So in particular, one of these galaxies is called Messier 87, M87. Okay. So I'm going to talk a lot about M87, which is why I thought I would introduce you to the family to which it belongs. Okay. Now, you saw lots of pictures of galaxies with beautiful spiral arms, but M87 seems to be more of a kind of spherical distribution of stars moving in 3 dimensions. You can see this, the very high density of stars here, and the density falls off. And that's reasonably well understood. These stars are orbiting in all directions, in all planes. Okay. And it's much bigger than our own galaxy. Okay. So astronomers use light years, but sometimes they use this unit called parsec, which is just 3.26 light years. Okay. So just to give you an idea of this, the nearest star is about 1 parsec away. The size of our galaxy is about 50,000 parsecs. The size of M87 is about 100,000 parsecs, right? But its distance is about 50 million parsecs, megaparsecs, as we say. Okay? Not 50, sorry, 20 million parsecs, 50 million light years. Now, I'm going to again change gears because I have to introduce you to the technique by which radio astronomers were able to study M87, and after a very long quest of nearly 50 years, were able to zoom in on the central black hole. So I'm going back to your basic optics. So here's the lens, and first look at this blue line. Think of it as a wavefront, or you can think of all these rays which are perpendicular to this, and the lens focuses them at this point. Okay. Now, according to geometrical optics, all the rays reach a single point. But we know that geometrical optics is not the full story. Light consists of waves. So therefore, this image actually has a finite size. And because of that, if you have light rays coming from a nearby direction, and if the two images overlap, then you may not be able to say that you have two objects. You may just say that there's one object. So this is the concept of resolving power. Okay, for any telescope or microscope, for that matter, there is a minimum separation of two objects where the two images can be distinguished. And so I'm giving you a very, very simplified account of what this resolving power is. So think of a wavefront which has some tilt with respect to the original wavefront. And the tilt is so chosen that the gap between these two wavefronts is less here, and it increases by just one wavelength. So that means the angle between these two wavelengths is one wavelength divided by diameter, lambda by d. So then what would happen? All these waves from the blue wavefront add up in phase here. Okay, and that's how you get a bright image. But from this wavefront, the phase varies continuously from 0 to 2 pi, or the path difference, as we call it in optics, varies from 0 to lambda, so they all cancel. Okay. So then these two can be separated, because where this creates a bright image, this creates a bright image somewhere else, but darkness here. Okay. So just remember lambda by d. I will skip this. It's a little more technical, but I will skip the mathematics. But what this tells you is that the same effect that you can get with a large lens, if you are able to collect the light waves before they enter the lens, A, B, C, D, right? Then it's up to you how you want to combine them. Okay, you could combine them to produce an image here. You could combine them to produce an image here. So I've just shown how this combination can be made in these equations, but you don't need these equations to understand what I'm telling you later. The principle is that instead of having a giant lens or a giant mirror, if you're able to collect the electric field, after all, light is an electromagnetic wave, from the entrance, then you can combine these in many different ways in order to get images of objects which come from different directions. The mathematical tool is Fourier transform. So that's for those of you who would like to read further. Now, this is the technique which was pioneered in Cambridge in United Kingdom, and it won the Nobel Prize for this astronomer Martin Ryle. And pretty soon, once he had established the principle of combining these waves from separate telescopes, a very large telescope was built in 1980, operating at wavelengths from 1 meter to 0.7 centimeters. And these radio telescopes are quite beautiful. And of course, my favorite is obviously this one, because I worked there for a decade and it's operated by National Center for Radio Astrophysics, right? Of course, these antennas look very small compared to the VLA antennas, but actually they are much bigger. It operates at longer wavelengths, 2 meters to 20 centimeters, which are much more difficult to observe from more advanced countries, because there's a lot of stray radio waves, whereas this was, at the time of construction of GMRT, quite a deserted area. So the construction was completed around 2000. And there are actually 45 such 45 meter antennas, 30 of them. You're only seeing a few. And the principle is the same. The signals from these antennas are combined and you can create an image of the sky. Okay. Now we move to M87. Okay. Now a number of pictures are combined here. So let's look here. This image is 25 kiloparsecs. So you're almost seeing, of course, the whole galaxy is 120 kiloparsecs, right? So this is the first radio images which you made. And you already see the radio emission is very peculiar. Okay. Radio waves coming from everywhere. Somewhere they're very bright and seems to be coming from some ring. So clearly something very strange is going on. Then we do some kind of zooming. Okay. So this was 25 kiloparsecs. Then this is the next picture. Okay. Let me see. Yeah. 800 parsecs, right? So you see some object in the center which seems to be sending some kind of jet in this direction. And although you don't see it, it's probably sending a jet in the opposite direction as well, because both these regions are showing evidence of a lot of radio waves. So that was the model which was created, that there's some object here which is sending jets. What is that object? Well, people thought of various possibilities, concluded it was a black hole, but that was only a model. It was never verified, okay? But radio astronomers did not give up. They zoomed in. So here is now 400 parsecs. So you can see the same VLA, you're going to shorter and shorter wavelengths, okay? Then just the central region has been blown up, right? Now you're at 300 parsecs, and you're again seeing the central region, which is sending out some material in the form of a jet, 0.8 parsecs. So this is now no longer VLA, but VLBA, I'll tell you, where you have to add more telescopes, same short wavelength, but greater separation between the telescopes. So lambda by d is smaller. So here are a few numbers. If you have 1 arc second, and let us say VLA is operating at 3 centimeters, the separation of the antennas is 30 kilometers. If you divide these two, you will get lambda by d in radians, right? And it becomes about 0.2 arc seconds. Now, at the distance of M87, 1 arc second is 16 parsecs. Okay. So arc second is an angle which is 5 times 10 minus 6 radians. So just multiply that by 50 million light years. So 16 parsecs is a pretty good resolution. But optical astronomers, of course, could see better. They could see down to a few parsecs. Okay. And they saw this cluster of stars, which I showed you, that bright concentration of stars in the center of M87. Okay. And these stars were moving very rapidly. So clearly, they were moving under the influence of a large central mass. Okay. And still, the radio astronomers assumed a black hole because of the energetic phenomena happening. The optical astronomers assumed a black hole because of the rapid motions of these stars. But the actual size of the Schwarzschild radius, you can scale up. If it is a billion solar masses, that is what is needed to explain the velocities of the stars and the energy coming out from M87. Okay. The Schwarzschild radius will be 3 kilometers multiplied by billion, which you can convert. It becomes almost 1 light day. Okay. So even the best observations with VLA are not able to get down to the Schwarzschild radius or event horizon. And it's a huge discrepancy, right? Between 16 parsecs and 1 light day. If you divide them, I'm sorry, they're in different units, but it's a factor of 18,000 missing. So a radio astronomer should have given up. But around the beginning of the current century, 2 people, one in Germany, one in United States, both at that time doing their PhDs, decided that, look, the same formula lambda by d tells you if you can go to a wavelength of 1 millimeter and make d 10,000 kilometers, then you will actually be able to get down to 1 light day. And of course, they proposed this experiment, and ultimately they joined forces. And these are not experiments that an individual can do. Okay, you need telescopes all over the world, and I'll explain the technique which they used. And when I say they, I mean they and their collaborators. The final papers had 300 authors, like I told you. So this technique is called very long baseline interferometry. I already told you that if you can get the electric field all over the wavefront, you can combine it as you like. Now in the GMRT and VLA, they are combined in real time. Okay, optical fibers bring the signals to a common point, and they are recorded and they are combined in a computer, combined with different ways to get the image in different directions. Okay, but if you have one telescope in Hawaii, one in Spain, one in the South Pole, one in Greenland, one in Chile, you cannot do this. You have to record these signals. Then how do you combine that? Remember, we are talking about wavelength of 1 millimeter. So the period of is 4.3 picoseconds. So when you record, you need the time to this accuracy. Okay. No, actually, even the GPS gives you time to a few nanoseconds. So there are very special techniques in VLBI. I can say a little more if people want to know how you keep the time and frequency accurate at all these stations. The data itself has to be used. So this explains why the data was taken in 2017 and the map was published only in 2019. Because these recordings had to be taken to a common point, played back on a computer, aligned times and all had to be obtained. So this is the best picture of M87 before this Event Horizon telescope. Okay. So this is pretty good. It's 30,000 astronomical units, which is 200 microarc seconds. And what they wanted to get down to, tens of microarc seconds, that's 40 or 50, 600 astronomical. So by now they had got to a factor of 5 of the final goal. And still you see the same thing, some central bright object and some jet coming out of it. Finally, here is the picture, which, as I already told you, and now it's called the shadow of the black hole. By zooming in to a resolution of, which I've given you on the previous thing, the one light day in some sense. And here's the location of the telescope. So this is a grand experiment. So instead of having, like GMRT has telescopes all over Junnar Taluk of, here are telescopes all over the earth. So Hawaii, Arizona. And you see a special problem that as the earth rotates, this is as viewed from M87, you will only get Hawaii and Spain together for a short time, right? Then Spain will set and Hawaii will rise. So this is an incredible experiment. These are pictures of all these telescopes. And I should tell you, these telescopes are not built for this experiment. Millimeter waves was important to astronomers because that's also the wavelength at which you can study interstellar molecules. And interstellar molecules, first you have atoms, then they form molecules in interstellar space, then they form stars and planets, and then of course they form life. Okay, so everyone is interested in studying interstellar molecules, and the giant telescopes were built to study it. One of the best is in Chile, this place. And in fact, without this telescope, this experiment would have been very difficult because it had a very strong signal which could be combined with all these other signals. I could tell you a lot more, but as I said, I can share this presentation and if some of you can read more. Okay. So this is the ring. Now, I've only given myself a little more time, 10 minutes, to tell you how the central black hole is able to emit such a strong jet and emit powerful radio waves, because it seems paradoxical, right? If light cannot escape from a region, how can it send out so much energy? By the way, this diagram simply tells you that because of the limitation I told you that you cannot see all the antennas all the time, this is a lens, like a giant lens, but it's a broken lens, okay? So even the image processing is not a simple problem. So here a little bit of simple physics, okay? Suppose I have two objects orbiting around a central object. And all of you know that this will move more rapidly than this. So, for example, in our own solar system, the Earth goes around at 30 kilometers per second, but Jupiter, which is much further away, goes around at 12 kilometers per second. But these are two adjacent rings. So this is going faster, this is going slower. Now, if they are rings of gas, then they will interact with each other. I mean, that's the process which you call viscosity. Okay. And therefore, the friction will try to move this forward and move this back. Okay. But what happens to an orbiting object if you apply a force in the opposite direction? I think you know this because all our satellites and so on, when they enter the Earth's atmosphere, they experience this kind of drag force, and then they spiral into the center. So the strange thing is that you have these two objects. Because of friction, this falls inwards and this falls outwards. And the net result is that there is a lot of heat generated by this friction, and the source of that energy is the potential energy of this object falling in. And that has enough energy not only to push this out, but also to generate a lot of heat. Okay? Now, this is a simple model, but this applies to gas going around a black hole. Okay, so maybe I will just stop by telling you about the efficiency of this process. If you take a certain amount of mass which falls and releases potential energy, this process can release around 10%. 10% of mc squared. So that is huge, because even the nuclear reactions release only 1% of mc squared. So that's why when you have an object which emits much more than what can be explained by nuclear physics, you go back to gravity. In fact, not only you go back to gravity, you go back to friction. So I like to say that primitive man generated heat by rubbing two sticks together, and modern astronomers generate heat by rubbing two rings of matter together. Now, there's still a long story about how this heat gets converted to radio waves or to X-rays, how it you need magnetic fields to produce radio waves, so on and so forth. But I think, and the last part I should tell you is that if you have, say, radio waves coming out from here, some of them will miss the black hole and come out, but they will get bent. Whereas if something comes too close, it will fall into the black hole. So that's why you get this shadow. So I had to go a little fast. So to complete the story, this experiment is continuing. It's such a large collaboration. I'm happy to tell you that I looked through the 300 authors. I found 13 people of Indian origin and 4 who had actually worked at Raman Institute. Okay. And I just want to say that this experiment pushed everything to the limit. The observing techniques, the computation, keeping of time and frequency, etc. So it's a great story in itself. There's a possibility. These millimeter wave antennas have to be put at very high places. So Ladakh is a possible location being discussed. And incidentally, the organization which is very keen on putting this antenna in Ladakh is ISRO. So I've finally made my connection with space. Of course, all the black holes and stars live in space, but here is also a connection with our own space efforts. And so thank you.
Thank you, Professor Rajaram, for this wonderful and insightful talk. Really, it's a very informative talk, especially for me. I'm also very interested to impart general astronomy as a multidisciplinary subject, especially for the biological science students also. Besides my own teaching assignments in the Department of Physics, I used to teach general astronomy. So, especially even in today's class in morning, one student asked me one beautiful questions about the when the astronomers and the researcher at worldwide, they came up with the first wonderful picture of the black hole in 2022. After that, most of the young generations is very keen to explore something, their passion about the black hole research and in the astronomy field. So my question with you, actually, you have already uh, gave a wonderful insights on the how the gravitational waves helps us to uh, explore the black holes, and you have also discussed about the event horizon. uh, can you give your insight on the singularity within the black holes?
Okay, this is a very difficult theoretical problem. The reason why it's a purely theoretical problem is that no, whatever is inside the black hole is not able to communicate with what is outside. Okay. However, the theory makes a clear prediction about the singularity. Singularity is not the event horizon. That's what I want to tell the audience. It's something within the event horizon where the gravitational force, first of all, the object which falls in will reach the singularity in a finite time. Okay. I mean, finite time as measured by the person who is falling in. As far as the person at infinity is concerned, it may take a very long time, but that's fine. And there will be all kinds of forces. And see, normally in a physical theory, if you have a singularity means that the mathematical functions become infinite. Okay, then you say you've reached the limit of validity of that theory. So the people who work on singularities, and there are many people in ICTS who do this, they're all theoretical people, naturally. They don't want to fall into a black hole. So they have to go beyond Einstein's theory of gravity and bring in quantum theory. So, to give an analogy, the original Bohr theory, Bohr realized that if you have an electron going around a proton, it will emit electromagnetic waves and it will fall onto the proton. And only quantum mechanics and later on the uncertainty principle prevents it from falling onto the proton. Okay. So similarly, people are looking for some quantum effects to prevent the singularity. But in spite of the efforts of hundreds of physicists over decades, there is no conclusive answer. That's what I would say. But there are many ideas. And again, as I said, if there are people interested, I can contact some of my colleagues who might be able to tell you more. Or actually, even better, ICTS records many of these lectures. So I can send the links. Already, if one of my colleagues has given a nice lecture on singularities, why not I send the link? I can do that. But it's not my area of expertise.
Yeah. Now I will bring you back on that question which has been asked in the morning lecture. That the most of the students, general audience want to know that if any kind of a thing cannot escape from the black hole, so how the image formed and how the brightness of that particular things can be seen, which have been shown in the figure.
Okay, so the answer is simple. We are not seeing anything coming out of the black hole. We are seeing material before it enters the black hole. Yeah. And that material has been heated to a very high temperature by these frictional processes, which I told you. And that radiation, because it originates outside the black hole, is able to reach us. So if you like, we are seeing radiation. But the same question can be asked about the gravitational waves also. You have the two black holes going around each other, right? And the gravitational waves escape because they don't come from within this. But finally, when you form a single black hole from it, after that, nothing escapes. So, right.
Thank you for your insight on this, and definitely the students which are listening you, they have an opportunity to learn from the experts. So I can take some questions from the audience as well. There is one questions. I'm just putting it on the screen. This is Kalpesh Tandale. Okay. The question is, how do exactly astrophysicists calculate mass of the supermassive black hole?
Okay. I think one good example was a Nobel Prize, maybe only 3 or 4 years ago, which was awarded to 2 scientists, astronomers, one in Germany, one in the United States. And they looked at the black hole in the center of our own galaxy, which, by the way, EHT has also looked at it, but I didn't talk about that. I talked about M87. The black hole in the center of our own galaxy is close enough that you can look at individual stars which orbit around the black hole. So just as we know the mass of the sun, because you can easily calculate it. Once you know that the Earth has an orbital period of 1 year, and you can just do mv square by r equal to gmm by r squared. And so essentially a similar calculation was done. Of course, as an experiment, it won the Nobel Prize because it was extremely difficult because the center of our own galaxy is 8,000 parsecs, 24,000 light years away. So to see individual stars orbiting at around that black hole required very high resolution, the world's best telescopes, new techniques. So that is how this. So the most cleanest method is to observe the orbits of stars around the black hole. And in the case of M87, you don't observe individual stars, so you do some statistical study.
Yeah.
Because you can't observe individual stars, that's too far away.
Thank you, sir. Thank you again. And it's my own curiosity. Can you give an insight on the possibilities of the wormholes and the white holes? Because it's also in a sequence when we study the black holes, a lot of things in the waves.
I would only say that the theory of those is not as well established as that of black holes. The equations of general relativity do allow these. That's absolutely true. But maybe not all solutions of those equations can be realized in our own world. So as of now, I do not know of any direct evidence for wormholes. But yes, certainly Stephen Hawking in his writings, he is not very fond of white holes, but people do talk of wormholes as well. Right.
Okay, thank you. And before concluding this session, this is also something in my mind because you have, spent, I think, most of your time spent in the radio astrophysics research,
Yeah.
and I think during your job and then during your research you have maybe encountered with a lot of technology development, and now we
Yes.
are living in the age of artificial intelligence. Can you give some insight to what should be the future and how the impact of AI and quantum computing, especially in the with the reference of the black hole research in near future?
Okay. I won't say specifically black holes, but it's. I can say that in the world all over, people are building telescopes at all wavelengths, X-rays, and so on. And these telescopes are gathering enormous amount of data. In fact, there are not enough astronomers to analyze that data. Okay. So even if you wanted to study black holes in galaxies, you have to. In the case of M87, there was a lot of evidence, but in other galaxies, even if you had observed all those galaxies, observed the velocities of the stars, you have got the data sitting on your computer. Who is going to sit and analyze it? So I think the trend all over the world is to feed this data to some massive artificial intelligence, machine learning kind of program, which will narrow down the possibilities and then study those objects. Because otherwise, the new telescopes which are being built, because of the technology you mentioned, they will generate images, terabytes of data every night. Okay. So yes, AI, ML and all is there. The other kind of technology is the technology of detectors. Okay. And there again, there's a lot of progress made. Otherwise, this work could not have been done, whatever I described to you. These millimeter wave receivers, which is why ISRO is also interested in it. ISRO is interested in technology. And some early work on millimeter wave receivers was done in RRI in the 80s, but that was an older technology. The newer technology ones, probably ISRO may develop, or other institutes like TIFR and so on may want to develop. So yes, a lot of hardware, a lot of cutting edge hardware and software is involved in astronomy.
Thank you, Professor Rajaram. Really, it's a wonderful interaction with you. And dear friends, I'm very thankful on behalf of Dolphin PG Institute that you being with us. And one thing is very prominently I would like to share with you with a very short notice. Professor Rajaram accepted our invitation to share his insight and the research with our audience, and really it shows his commitments for the science in this country. So thank you very much, sir, for being with us and share experience in the research, especially with your black hole, which you have experienced during your research. And really, it's a wonderful talk. We are very much thankful to you. And the anonymity of the astrophysics and the any research, science research, science-based research, the more we do, more things remains to be done.
That's
So
true.
it's always possibility to improve the technological aspect, improve our understanding of the cosmos and the universe as well. So it's our appeal and it's our request to young generation. If they will observe the nature, definitely they will once one day in the near future they will have some elevation towards the exploring the universe and different kind of aspects which they want to explore in near future. So, with these words, I would like to thanks once again all the audience and students, the faculty members,
Mm.
which we have connected across the country, as well some participants from the globe, from outside of the country. So, I
Nice.
would like to thanks big thanks
Mm.
to all. And once again, big thanks to all and namaskar. And Professor Rajaram, it's our request whenever you visit
Mm.
Dehradun, definitely let us know. We
Sure.
would like to welcome you in our
Mm.
in our campus.
Sure,
Definitely,
sure.
sir.
I
Thank you
went
very
to the
much.
website and certainly looks very interesting. And
Yeah, yeah,
one should also thank the students for their
yeah.
attention. And if there are any later questions, also you can send it to me. And if anyone wants some references or links, I can send. Okay.
Yeah, yeah. And
Huh?
sir, one
Okay.
thing I would like to mention that we are settled in the foothills of the Himalaya, and the
Mm.
uh, opportunity of the exploration of the universe and the night skies, we are more
Mm.
privileged in that aspect.
That's true.
So I always motivate the students
Mm.
which are residing in this area that they have a greater opportunity to explore something related to the astronomy and astrophysics because they are well privileged to observe the night sky as we are not having such kind of experience in the metro cities nowadays.
You're right.
So thank you very much.
Okay.
So we are signing off until we meet again. Thank you very much.